Top-down design is the process of breaking a main problem into smaller parts and breaking those parts down further until each one is simple enough to solve directly. A structure diagram is the visual tool that shows that hierarchy, the whole system at the top, its major subsystems below it, and their components below those. This is decomposition from the computational thinking lesson, drawn. And the word the syllabus uses for those parts is subsystems. A system is decomposed into subsystems, each of which does one identifiable job. The example on the page is a smart alarm clock. At the top, the whole system. Below it, 3 subsystems: set alarm, check time, trigger alarm. And below those, their components. Set alarm breaks into input time. Check time breaks into compare to current. Trigger alarm breaks into sound buzzer. Read it downwards and you are moving from what the system does to how it does it. Read it upwards and each level answers the question, why does this exist? That two-way readability is what makes a structure diagram useful for explaining a system to somebody, and it is also how you check your own. If a box's parent does not explain why the box exists, it is in the wrong place. Now the part exam questions actually ask for, and it goes beyond naming the boxes. Each subsystem should be described in terms of its inputs, its processes, and its outputs. Look at the table. Set alarm. Inputs are the hours and minutes entered by the user. Processes are validating that the time is in range and storing it. Output is a confirmation on the display. Check time. Inputs are the current time from the clock and the stored alarm time. Process is comparing the two. Output is a signal when they match. Trigger alarm. Inputs are that match signal and the volume setting. Processes are starting the sound and beginning the snooze timer. Outputs are the buzzer sounding and the display flashing. Now notice the thing that makes this worth doing rather than a formality. One subsystem's output is the next one's input. Check time produces a signal. Trigger alarm consumes it. Writing the inputs, processes, and outputs for each box is how you discover whether your decomposition actually joins up. And if a subsystem needs an input that nothing in your diagram produces, the decomposition is incomplete, and you have found that out on paper rather than halfway through writing the program. 3 rules, and the second one is the one that catches people. Hierarchy. The parent module is above, the children below, and the relationship is part of rather than happens after. No logic. Unlike a flowchart, a structure diagram does not show decisions or loops. There are no if boxes and no arrows looping back. It shows the components of a system, not the order in which they run. That is the distinction to keep clear. A flow chart shows sequence, a structure diagram shows composition. If a question asks how the system is broken down, that is a structure diagram. If it asks what happens in what order, that is a flow chart. And modularization. Each box is a discrete task that could be written as its own subroutine, a function or procedure, which is exactly the link to topic 8. A question students reasonably ask: how far do you decompose? Stop when a box is simple enough to be implemented directly, when you could sit down and write it as one straightforward subroutine without needing to plan it further. Going beyond that produces a diagram with more boxes and no more understanding, and it can actively obscure the design. Going less far leaves boxes that still hide real complexity, and you discover that only when you try to write them. A practical test: can you state the inputs, processes, and outputs of the box in one line each? If yes, stop. If the processes column would need a paragraph, that box has more than one job in it and should be broken down again. That test also happens to be exactly what the exam asks you to produce, so it is worth applying by default. The advantages of designing this way, and each has a concrete reason. Easier debugging. Finding a fault in a 10-line module is far easier than in a 1,000-line program, because the search space is small and the module can be tested on its own, which is the iterative testing from the first lesson of this topic. Collaboration. Different programmers can work on different modules simultaneously, which is only possible because the interfaces between them were defined in advance. That is what the inputs and outputs columns really are. A contract so that 2 people writing 2 modules can work separately and have the results fit together. Reusability, a module that works can be used again in another program or elsewhere in the same one. And easier maintenance, a change to one module does not disturb the others, provided its inputs and outputs stay the same. Notice how much of that rests on the interfaces. Modularity is not just cutting a program into pieces, it is cutting it into pieces that meet along known boundaries. 4 things to take into the exam. First, a structure diagram shows the hierarchy of a system, not its sequence. No decisions and no loops, and saying so distinguishes it from a flowchart. Second, when asked to decompose a system, produce subsystems that each do one identifiable job and be prepared to break them down one further level. Third, describe each subsystem by its inputs, processes, and outputs, because that is the form the mark scheme uses, and it is more than just naming the box. And fourth, when giving advantages of modular design, attach the reason, easier debugging because each module can be tested independently, and parallel working because the interfaces were agreed in advance. The reason is what is being marked, not the term.